My name is Vaishnavi. In this project, I implemented an unsupervised anomaly detection system using an autoencoder neural network in TensorFlow to identify abnormal thyroid conditions. The goal of the project is to train a model that learns the patterns of normal thyroid data and detects unusual or abnormal samples using reconstruction error. The approach is widely used in real world applications such as fraud detection, industrial fault detection, etc. In this project, I use the UCI thyroid disease dataset, and the implementation is done using TensorFlow, scikit-learn, pandas, and matplotlib. The dataset used in is the UCI thyroid disease dataset, especially ANN train data, ANN test data. The dataset contains 21 numerical features, one class label. The original class represents thyroid condition. Class 1 for normal, class 2 for hyperthyroid, class 3 for hypothyroid. For anomaly detection, we convert these labels into binary format, that is normal to 0 and anomaly, which is 1. So in this project, class 1 comes under normal and class 2 and 3 are treated as anomalies. Now let's have a look at the notebook file. You can run this in Google Colab or in your Jupyter notebook as well. So let's see. The first step is importing libraries. In this step, we import the required libraries like Python libraries like pandas and numpys for data manipulation and numerical computation, matplotlib and seaborn for visualization, scikit-learn for pre-processing and evaluation metrics, TensorFlow and Keras to build the autoencoder neural network. These libraries provides the tools needed to load data, pre-process it, train the model, and evaluate its performance. Next step would be uploading the dataset. Since this notebook is executed in Google Colab, we upload the dataset using the files.upload function. You can see here. This allows us to upload the training and testing files directly into the Colab environment. Next, load the training and testing data. In this step, we load the dataset using pandas. The files are space separated, so we specify the separator when reading the files. We create two data frames, one for training and another for the testing data. And the step 4 is dataset overview. Here we can check the shape of the dataset to understand the number of samples, features. This step helps confirm that the dataset has been loaded correctly. Separate features and target. The last column of the dataset is represented as the class label. So we separate the dataset into X, which has the input features, and Y, which has the target variables. This is a common pre-processing step in machine learning workflows. And next step is converting the labels to binaries. Since the dataset originally has three classes, we convert it into the binary labels. Here we map class 3 to normal, which is 0, class 1 and 2 as anomaly for 1. This allows us to treat the problem as binary anomaly detection. And next step is the feature scaling. The neural network performs better when the input features are normalized. So we apply standard scaler to standardize the features so that mean equals to 0 and standard deviation equals 1. This helps improve training stability and convergence. Next is filter normal data for training. Since this is unsupervised anomaly detection, the autoencoder must learn only the patterns of the normal data. So we filter the training dataset and keep only the samples labeled as normal. The model will then learn the structure of more normal data and later detect anomalies based on reconstruction error. Building the encoder. Here we define the autoencoder architecture. The network consists of an encoder, a bottleneck layer, a decoder. Here you can see the architecture used. The encoder compresses the input into a smaller representation and the decoder reconstructs the original input. The model is compiled using an Adam optimizer, mean square error loss function. Next, training the model. In this step, we train the autoencoder using only normal training samples. We also use early stopping, which stops training when the model stops improving. After training, we plot training loss and validation loss to monitor the learning process. You can see how it varies. And next, reconstruction error. After the training the model, we pass the test data through the autoencoder. The difference between the input and reconstructed output is called as reconstruction error. Normal samples typically produce low reconstruction error, while anomalous samples produce higher reconstruction error. And determining the anomaly threshold. To classify the anomalies, we define a threshold. In this project, the threshold is determined using the 99th percentile of the training reconstruction error. Any sample with the reconstruction error above the threshold is classified as anomaly. You can see that the anomaly threshold value is 0.18. And model evaluation. We evaluate the model using precision, recall, and F1 score. And also we represented it using a confusion matrix. Here is a representation of confusion matrix. Now let's go for reconstruction error distribution. And this plot shows the distribution of reconstruction errors of normal and anomalous samples. The red line represents the anomaly detection threshold. The samples with errors beyond this threshold are classified as anomalies. And latent space visualization. So in this step, we visualize the encoder representation using a PCA. A PCA reduces the high dimensional latent features into two dimensions, so we can visualize how the model separates normal and anomalous sample. Here is the visualization. And to conclude this project demonstration how autoencoders can be used for unsupervised anomaly detection. The model learns the patterns of normal data and detects anomalies based on reconstruction error. This approach can be applied in various real world applications such as fraud detection, industrial monitoring, and healthcare diagnostics. Thank you for watching the video.